Bismillah ar-Rahman ar-Rahim. Today we are going to discuss one important concept in thermodynamics, which is called entropy. And this concept is difficult, and there are many ways to explain this concept. Dr. Salim will talk also about the second law of thermodynamics, which is the second part of this important concept. Entropy was introduced because some scientists, they could not explain why processes happen only in one direction. Most processes happen in one direction. Let me give you an example. They call them one-way process. A one-way process, if you take a glass in your hand and then you drop it on the floor, the glass will break. Okay? You can never see a broken glass getting together and becoming again a glass. That's a one-way process. Another example of one-way process will be ice. If I take a piece of ice and put it on the table here, after sometimes it all becomes water. This is also another one-way process. It can never spontaneously, the water becomes by itself without external actions. By itself it becomes ice again. So these are called one-way processes, and these, by the way, these one-way processes, they don't, if you go back the other way, it doesn't violate the first law of thermodynamics, which is the conservation of energy. But so people wanted to know why these processes are only in one direction. So the direction of the process, so I give you the example of one-way process, which is ice melting. Okay, that's a one-way process. Breaking of a glass, that's also a one-way process. And this one-way process are actually, the direction is determined by a property called the entropy. Okay, so the direction of these one-way processes, the direction is the direction of the process itself is determined by a property, by a new property, which is called the entropy, okay? Called the entropy. So we call this property which gives you direction of the process, we call it the entropy. The entropy. And the letter for the entropy is S, okay? Like there was a specific letter for the internal energy, which was E, and now we call it the entropy. It gives you the direction of the process. Now let me define the entropy, okay? Definition of the entropy. So what is the entropy? Okay, what is the entropy? The entropy is a measure. One of the definitions, there are many of them. There are many definitions. One of them is a measure of disorder. Okay, disorder. As you have seen, when the breaking or the glass breaks, there are more disorder now in our system. When the glass was a piece of glass in your hand, it was more ordered. When it falls from your hand and break on the floor, there is some kind of disorder. So the entropy is a measure of disorder. Another in a system, disorder in a system. My system here was the ice. Of course, when you have the ice, all the atoms are very close to each other, occupying a small volume, and then when it melts, okay, it becomes water. The molecules are much farther away from each other, and you have more disorder. So the entropy is a measure of disorder. So again, the direction of these processes, which are called one-way processes, are determined by a new property which is called the entropy. And the entropy definition, one of the definition is a measure of the disorder. The other definition, the entropy is called the arrow of time. Okay, the entropy also is called, another definition is called the arrow of time. As you know, time always increases, and the entropy of an isolated or closed system also increases, okay? So we call it, the entropy is the arrow of time. So time increases, always increases, and therefore the change in entropy, or the entropy of a system, a closed system, the entropy of a closed system, the entropy of a closed system always increases, okay? Always increases. So again, these one-way processes, they have a name. They call them irreversible processes, okay? So these one-way processes, they call them irreversible processes. So all natural processes, all natural processes are irreversible. It means they are always in one way. Okay, they are always. So when the breaking of the glass happens, the glass cannot come back to itself and become again a cup of glass or so. If the ice melts, it cannot becomes ice spontaneously without any outside intervention. Okay, so we call them irreversible processes. Let's write now in all irreversible processes. In all irreversible processes, the entropy of the closed system where the process is irreversible always increases, okay? That's an important statement when we talk about entropy. So it never decreases, okay? There is one mathematical definition of the entropy. So let's go to the mathematical definition of the entropy. Is that the change in entropy of a system, the change in entropy, delta means the change in entropy of a system, which means S final minus S initial is equal integral of dq reversible over T. Okay? dq reversible, so we're talking about irreversible processes, where reversible processes are two-way processes. It's actually most of our processes, daily life processes, are irreversible. So we have to find, to be able to calculate the change entropy of the system, we have to find a reversible process which is similar to the irreversible process that we are talking about. Okay. Now entropy, of course, the SI units of this will be joules per Kelvin. Okay, and entropy is called a state function. Okay, entropy is a state function. Entropy is a state function, just like the internal energy. Okay, a state function. It means it depends only on the initial, depends only on initial and final states. Initial and final states. It means it's path independent. In other words, if you want to write another statement for this, you can say that it is entropy is path independent. Entropy is path independent. So if somehow, okay, if somehow I can now draw a PV diagram here for you, and a PV diagram. If I know the entropy in a state I call it SI, and I know the entropy in a state F, I call it SF. If I go through this process here, let me show you a process. If I go through this process here, okay, through this process, and number one, and I calculate delta S, so I will have delta S 1, and I go through this process here, a different path, number 2, and I calculate delta S number 2, I found them to be equal. because it is the same initial and same final states. If the initial and final states are the same, then whatever path you take, delta S will be the same, and we call this a state function, and the change in entropy will be the same. Okay. Of course, work and the heat are path dependent. We cannot write that the work for this process and the work for this process are the same. No. Or the heat for this process and the heat for this process are the same. But we can say that the change in entropy for this process and this process are the same, and we call them a state. We call this a state function. Okay, let me go back here. This is one of the definitions of the change in entropy. This is, the form, the mathematical form. Actually, this is the thermodynamic definition of the change in entropy. You can see it's related to the exchange of heat of the system with the environment and temperature of that system. There is another definition which is called the statistical definition of entropy, which will not be covered in this course, but there is another way to calculate the change in entropy through statistical definition, and this is the thermodynamic definition. Now, let me give you an example, the first example, which is called the free expansion, and see how we can calculate the change in entropy for a free expansion. So example here, which is called what we call the free expansion. And this is a very important example because it will illustrate for you so many things. So let's draw a PV diagram here. So, and imagine that you have a container here, which is insulated or isolated from the outside world. Okay, it's isolated. When I do this, I mean isolated, and there's a partition here. So we call this partition. And on this side we have vacuum. Okay, and here we have a gas. On the right side, on the left side, we have a gas. Okay, these are the gas molecules or gas atoms here. So there's a gas here. Okay, and this is the initial state. This is the gas state is represented on the PV diagram here by I. Okay, all right. So I'm going now to open the partition. So I'm going to open the partition. Okay, so the gas has an entropy here. In this case, SI, okay? I call it SI, okay? And entropy in that case. Now I'm going to somehow I'm going to remove the partition, and this is vacuum here, remember? So what will happen? Of course, the gas is going to expand. So if the gas expands, of course, when the volume is small, the particles, their whereabouts, statistically we know where they are, the particles, because the volume is small. As we remove the partition, the volume becomes bigger, and the particles, they have more freedom to move, and statistically, the disorder becomes more, because it is more difficult to know where they are. So if we draw now again this partition, the container again without the partition, because we have so we remove the partition, the gas will going to expand. Of course, the gas, when it expands, it doesn't do any work, because the other side of the container is vacuum. Okay, it doesn't do any work, the gas to expand. And since the system is isolated here, as you can see from the outside world, there is no heat exchange. So in this problem, we have two things. We have work done by the gas to be zero, because there is no work done, this is vacuum, and there is no heat exchange with the environment. From these two, we can conclude that delta E internal of the gas will be zero, because the internal is Q minus W, so it will be zero. And from this, we can conclude that the temperature of the gas is the same, didn't change during this expansion of the gas. Of course, the gas here expanded in the whole volume, and of course, if we have more expansion, the gas molecules will have more freedom to move, the entropy will increase, because we have more disorder in the system. Here there is more order than here in this case. And we can represent this by a final state here, where the volume has increased, you can see, and the pressure should decrease naturally, it should decrease. So this is the initial and final state. However, we cannot draw the PV, the path joining I to F. This is I and this is F. We cannot draw that path because we don't know exactly the state of the gas at any point. Pressure, volume, we don't know between the points between I and F. So the idea is this. Now, since the entropy is a set function, I have to find a reversible process which start and ends at the same points or the same states as this free expansion. Okay, what is, according to you, my son, when you see that T initial equal T final, what will be the process that will cross your mind that will have the same T initial and T final? I think it will be an isothermal process. So if we draw here an isothermal process, okay, and actually it's an expansion because we see that the volume has increased and therefore the pressure will decrease. So this is the isothermal process. Now, I can now, because I know the path, exactly I know the process, what it is, I can now calculate the change in entropy for this process, the isothermal process. And let's use the equation which was written here, delta S equal integral of dq over, remember here, dq reversible. So the isothermal process is a reversible process. Yes, this is a reversible process. As long as I can draw the PV diagram, the path itself, it is reversible, okay? So let's now calculate delta S for that, for the isothermal process, okay? Using the equation, the equation we have written before. So let's write it down. Let's write it down again. And then we are going to use the fact that the change in entropy is path independent, and then we can find the change in entropy for this free expansion. So delta S in this case will be integral between the initial state, okay, and the final state of what? Of dq reversible, which is the isothermal process. Since T is constant in this process, the isothermal T is constant, I can take it out of the integral, and dq will be Q over T. So what is the heat for the reversible process? Please, my son, go back to old videos and look at the heat exchange in the case where you have a reversible isothermal process. Is nR T ln of V final over V initial. Don't forget to divide by this T here. And this T and this T are the same. They will cancel out, and you end up with NR ln, okay, NR ln of V final over V initial. So if I know the number of moles in the gas, and I know this is my initial volume, and this is my final volume, if I know this volumes, number of moles, I can calculate exactly what is the value of delta S for this isothermal process, which is connecting the two initial and final states of the free expansion, which is irreversible process. Now we are going to use the fact that since delta S is a state function, okay. So I can say that this is for reversible, all right? For reversible. That delta S for the isothermal process that we just calculated is equal delta S for the free expansion, okay? And of course, the free expansion is irreversible process. So you see how we managed to get the delta S for an irreversible process by knowing the delta S for a reversible process by doing, of course, this integration here. Okay, so then I can write here that delta S for that free expansion, which is irreversible process, is also equal to NR ln of V final over V initial. And this is very important result that you should know it. Of course, you will notice something important, that if I remove the partition, the gas will expand, and the gas will never by itself spontaneously go back to this situation here. It's a one-way process. It is irreversible process. And for delta S, for irreversible process, is always positive because the entropy increases, okay? And this is positive number here because the entropy increases. So S final is greater than S initial, and delta S will be positive in this case. Okay, so let's see what did we benefit from this example, free expansion. So as a general rule, to find the change in entropy for irreversible process. Why we are saying this? Because for irreversible process we cannot integrate. We cannot find the change in entropy using this equation here because we don't know the path connecting the initial and the final states let's say on the PV diagram. So to find the change in entropy for irreversible process occurring in a closed system, see our system was closed, replace that process, that irreversible process, which is the free expansion here, as an example, with a reversible process. What was the reversible we used? It was the isothermal process. Remember the green line here. So replace with a reversible process that connects the same initial and final states. Now, when my process is reversible, I can use this equation to calculate delta S. So now calculate the entropy for that reversible process using this equation here and equate it, you see, equate it to what? To the irreversible process. So calculate the change in entropy for that reversible process, which is in this case the isothermal, and equate it to the irreversible process, which was in this case the free expansion. They have the same equation. Why is that? Because S is a state function. It depends only on the initial and the final. As long as the two states, the two processes have the initial and final, the same initial and final states, then you can do this method here. Thank you.